introduction. Well, we thought we would deal with two aspects of wind at height. In fact, Anthony Wood had suggested a title somewhat along these lines, and we thought it was a good title, actually. So we stuck with it, and we're going to have a bit of a tag team here. I'm just going to introduce our talk, and we are dealing with wind both as the friend and as the foe, and we're going to begin with the foe bit. So I think at this point I'll hand over to John, and then I'll pick up the other bit, which is going to be treating wind as the friend.
Well, if we think about wind as the foe, it's mean, it's nasty, it causes us all sorts of problems. Structural loads sometimes are excessive, causing problems for foundations. There's problems with excessive building motions in some cases, causing discomfort to occupants of tall buildings, which has to be sorted out. There's some optimization of structures that has to take place and very early on in design, and you need the input from wind tunnels to do that properly. It's an iterative process, it takes time. Wind can cause high local suctions or pressures on building facades, which we have to design for, and can have negative impacts on pedestrians as well. We'll just go into the relationship between wind and height. I think everybody so far has had a similar slide, but essentially, as height increases, the importance of wind loads increases in the design. Today, here in Dubai, there's the Burj Dubai. It's unprecedented height. There's not a lot of information out there that in codes, for instance, that tells you what's going on above several hundred meters in height, and you need to get some sort of expert advice. We've worked on that building, but a number of other buildings here in the Middle East and in Europe and the United States. One of the main problems on high-rise or super tall buildings is vortex shedding. The shedding frequency of vortices is related to the wind speed, the Struhl number of the body or the floor plan you're looking at, and the width of the building. In the plot on the lower right, you see two curves, a dash curve, which is the response of the building if there were no vortex shedding, and the kind of a bump you see on the plot is the vortex shedding response. So at a given wind velocity, the vortex shedding response can add quite a lot to the dynamic fluctuating loads on the building. Now there's if that wind velocity happens to be a region where you're operating in your design, then you want to either eliminate that problem or move it somewhere. You can move that through stiffening the building and changes in the structure, but that can often be a very expensive option. So one strategy is to try and reduce the amount of vortex shedding. One way of doing that is through shaping strategies, softening the corners of your building's geometries, introducing tapering and setbacks, which is something the Burj Dubai does to good effect, varying the cross-sectional shape, introducing spoilers or almost like strakes on chimneys, that type of device. To effectively, all these strategies are means to reduce the magnitude of the forces being applied to the building due to this vortex shedding problem. Another way is introducing porosity or openings into the building. We'll just run through a few examples here. The Burj Dubai is an obvious one where tapering, changing the cross-section, even in early stages, changing the orientation of the building were all ways we could sort of fight against our foe. This is an example, and particularly relating to the accelerations of the building. The top curve, or the top bar graph, is a plot of the probability of, or the percentage of time of winds of a particular strength, 31 meters per second, and for different wind angles. Then the bottom plot is the accelerations at the 1 and 10-year wind speeds. And the interesting thing, which we were able to do early on, was orient the building in such a way that the wind directions causing the high accelerations were oriented with wind directions where there's fairly low probability of high winds. So that's beneficial to the structure. And that is one strategy. If you get advice early enough on in the design, then this is something that can be done. One problem as we go super tall is there's very little information about the wind speeds and turbulence at high levels. This is an example of the wind climate over Dubai. That's one particular event in 1988, Shamal winds, and it basically shows how variable the winds are at that height. This type of study, the forecasting tools that we use, it gives us an idea of the way velocity changes with height. It's quite important. The next slide here is the tapering effect on the Petronas towers. Again, not sure that it's intentional, but it's certainly beneficial in terms of the response of the structures. The Taipei 101 building, that was an example where we were able to play with different corners. As it was originally tested, the crosswind motions of the building were quite severe, and through various types of corner options, we were able to come up with a solution that was pleasing to the architect, yielded, it was a compromise between the amount of net lettable area of the floors, what the architect could live with, and what we as wind engineers could recommend. But the end result was a 25% reduction in the base moment. That change wasn't enough to give suitable accelerations for the building, so there was additional works taken out. This is an example of the damper that was used to control, or an image of the damper that was used to control motions on the building, to bring accelerations down to reasonable levels for the occupants. Again, this 25% reduction due to the corner geometry and a 35% reduction in the fluctuating response due to the damper. The Chicago Spire, something recently tested in our Canadian office, shows both tapering of the building and twisting, which is like the spoilers or the strakes that was discussed earlier. It's an interesting building, very tall building, very long periods of vibration. The fundamental modes of vibration, the periods were on the order of 13 to 14 seconds. The second modes of vibration were in the neighborhood of 5 seconds. So they're both modes are excited by the wind. So it's something we had to look at in more detail than would be done on a sort of mid-rise, or what we would traditionally think of as high-rise buildings. One of the things we were able to do, and these are some interesting plots, and there's a lot in them, so I'll try and explain what's in them. The green bars on the right-hand side of the plots gives you an idea of the number of residents per floor in the buildings. That's the values on the lower axis of the plots. And on the vertical axis, the number of floors. The red bars you see is the number of residents per floor that would perceive motion. So a level of accelerations of about 5 millig's. So on the left, you see the fundamental modes in red. On the right, you see the higher modes in red. And the little yellow bars are the number of residents that might perceive motion if we could use something like an active mass damper to control building vibrations. So we can reduce the number of people from 5 or 6 at mid-level down to basically none in the higher modes, and in the fundamental modes, upwards of almost 50% of the occupants of the top floor perceiving motion to perhaps 1 or 2. There's a couple of ways of assessing building motions. There's an ISO criteria that many are familiar with. One additional measure that was taken for the Chicago Spire was to use moving room simulations, and this is tests we undertook at a Canadian lab, a university that actually does research into ship construction, and they had a model of a bridge that could be excited. The picture on the right shows a few of our staff, and actually the ladies in the chairs are the people that are responsible for selling the residential units in the Chicago Spire. So we thought it would be important to have them there because they have to be able to explain to some fairly wealthy individuals, I imagine, just how comfortable the environment will be. So we were able to subject them to the sorts of motions they would expect without damping and with damping to give them an idea of what sort of level of comfort their customers can expect. This is an example of a liquid column damper again. Wind can be a foe, but we can make friends, if you like, and we can use some fairly economical ways of doing that, using existing water storage tanks on the top of these high-rise buildings. They can be tuned to the same periods of vibration of the building and reduce the fluctuating motions of the building. So, that's great. Wind tunnels can help you, but just how good are wind tunnels anyway? That's probably a question a few of you have asked. Well, I can tell you a little bit about that. I've done some of my PhD research was on a project called the Chicago Tall Building Study. So we looked at 3 tall buildings in Chicago, monitored over a period of about 5 years. Fairly significant buildings, all significant on the Chicago skyline, certainly. I've referred to them as buildings 1, 2, and 3 here to keep some sort of anonymity, but anybody that knows anything can probably figure those out. But the table on the bottom, I've got frequencies of vibration and measured the range of measured damping we've gathered so far in the 5 years. My part of the studies are over, and I was granted my PhD, thankfully. But the interesting thing here, buildings 1 and 2, buildings 1 and 3, quite light buildings, quite low damping in the fundamental X and Y sway directions. These are the sorts of displacements you'd expect maybe on an annual basis. Buildings 1 and 2, buildings 1 and 3, quite light buildings, quite low damping in the fundamental X and Y sway directions. These are the sorts of displacements you'd expect maybe on an annual basis. Building 2 is a concrete building, slightly higher damping, which I think is of interest. So how do we stack up compared to full-scale measurements? Well, the dashed black lines in there is the range of, this is data from a particular wind event measured during the studies, and the X's in the plot are the actual measured values. The dashed lines are the wind tunnel predictions during that event, so the likely range is somewhere in between. The red line is a regression curve through there, so I think what it shows on average is that the wind tunnels can do a good job of predicting full-scale responses. So I think at that point, we get into wind as a friend, and Peter will take over.
Okay, I guess I'm a friendly kind of guy, so I enjoy this part of the talk. Well, we've heard from Roy about wind energy, so we'll talk a little bit about that. That's obviously one area where wind could potentially be a friend. It can help remove heat from the building through double-skin walls. There is a potential to use it for natural ventilation, which Peter Weissmantel had referred to, I think. And one other aspect where it could be used is for having perhaps more comfortable outdoor spaces at height. We've heard about the reduction in temperature that you get as you go up in height. And so if you can create outdoor usable spaces at great heights in a hot climate, that could be beneficial. And also down at ground level, there's a potential there for increasing the breeze in very hot areas, in tropical areas where there may not be a whole lot of wind and it might be very hot. So if you can be in shade and have a breeze, that'll help. Well, thinking about wind turbines, as Roy pointed out, the first thought that comes to mind is we'll put it right on top. That's where the winds are high. He explained the velocity cubed relationship. So clearly there is more power available at height. However, one thing that also is pointed out from this relationship is that if there's any disturbance in the flow, such as other buildings nearby, that also is going to have a big impact on the wind power. So if you take an example of a 41-story building, we just took one building that we tested in Rochester, New York, 137 meters high, 52 meters wide by 23 meters in the other dimension. And it's in a wind climate similar to that of Rochester, New York, where the average wind speed is 4.5 meters a second. And so let's assume the turbine center is 30 meters above the roof, and it's got a diameter that's equal to the width of the building, 52 meters. That's a big turbine. The building's located in a suburban environment, and so there, if we extrapolate using normal boundary layer assumptions up to the height of the center of the wind turbine, our wind speed has gone up to 5.79 meters per second. So if we assume we've got a fairly efficient turbine, which means we can get a total of about 40% efficiency, the fact that you're limited already to having a maximum theoretical of around 59%, that tells us that we're going to get about 1.6 megawatt hours per year, and which equates roughly to about 12% of a building like that's requirements, if it's an average current building. Now obviously if you tighten up on all your other energy usage in the building and make it a much more efficient building, well then the percentage that you're going to get out of the wind turbine is going to go up. But that was a big wind turbine. I think one message that comes out of this is that if you're going to use wind power through turbines, then it probably needs to be considered as one of a series of different strategies to improve the energy efficiency. Wind turbines have been proposed on a number of buildings. We looked at them on an early version of the Freedom Tower design, and there, in order to give the wind access to the wind turbines, they were embedded in a very open cable type structure. One of the issues that we did identify before the design was changed was that in-cloud icing can be a problem on these kinds of structure. So once or twice every winter you could get a substantial accumulation of ice on a structure like this, and then when it melts it falls to street level, which is of course then a hazard to the surrounding area. But this does occur on some buildings already in places like Chicago and New York, and they close off the streets in the area until the problem is over. On the Pearl Tower in Guangzhou, the wind turbines there were embedded lower down in the building, and so one of the issues you have to look at here is, can you shape the building in order to guide the wind into them for a wider range of wind directions, because clearly there's going to be some wind directions where they will not work. And also the surrounding buildings can have a big impact, as we learned on this project. I don't have a lot of time to talk about facades, but RWDI does have a suite of software that we use internally, which we've named RWDI Skin, because this is a complex problem dealing with all of the convection, conduction, radiation, airflow issues that can occur within a double-skinned wall. And it requires a lot of careful study to make sure it's going to work. And you also have stack effects superimposed on these, causing changes in the infiltration and exfiltration, and you're probably going to need CFD to really understand what's going on. One can think of using the wind directly for natural ventilation, and these diagrams show different possible schemes. You can have simple wind driving airflow straight through the building. You can make use of some of the temperature gradients within the building. One of the problems that arises with really tall buildings is that you have stack effect. And this means that if you have vertical shafts, like elevator shafts running up the building, and you start giving the occupants options to open the windows in their unit, when they open a window in their unit, they're going to affect a whole lot of other units all the way up the building, which makes use of offerable windows and offerable vents by the tenants or occupants difficult. Though there are ways around that. For instance, one can make the shaft at ambient temperature. Then your elevators would have to be air conditioned individually. That way you can avoid the stack effect problems, and it opens up many possibilities for using natural ventilation. This idea of compartmentalizing the tower vertically was used on the Commerce Bank Tower. To make sure this kind of system is going to work, you have to bear in mind a number of variables. There's the wind direction, its strength, temperatures, the differential loads within the building, sources of heat from machine equipment and people. You need to look at a number of possible scenarios with temperatures and wind directions and pressures, and the occupant behavior, the way that they're going to respond. And generally, it's best to do pretty thorough studies if you're going to use one of these systems. We used the wind tunnel studies and CFD studies for Commerce Bank. At ground level, tall buildings have got a bad name in some places for bringing strong winds down to ground level, causing problems for pedestrians. In a hot climate, this can actually be beneficial, but you need to make sure that the winds are not dangerous, obviously, and also you need to provide shade in a hot climate if they're going to be thermally comfortable. As you go higher up, the air is going to be cooler, which is good in a hot climate, but the winds are also going to get pretty strong up there. And so you do need to have mitigation devices. These show some of them that were worked out for Burj Dubai to try and reduce wind speeds up on these upper terraces and also down on the lower terraces to make them more usable. But these terraces can be made into pleasant outdoor spaces, so there are opportunities there with tall buildings for getting nice outdoor spaces at elevation. And finally, back down at ground level, the idea of having openings at the bottom of the building to allow air to flow through and use the shade that you get down there as well can provide more comfort in hot areas. So to conclude, the shape of tall buildings can be formed to dramatically reduce wind loads. We've seen wind loads from vortex excitation, the peak that John showed, being like 2 or 3 times what you would get from a building code type calculation. If you can eliminate that, then you can dramatically reduce the wind loads, which of course reduces construction materials. This is generally done with wind tunnel testing. But these kind of factors need to be considered right from the outset if you're going to a super tall building. Otherwise, you could have backed yourself into a corner for which it's difficult to extract yourself later on. Supplemental damping systems are an important part of the overall structural design. and should be treated like stiffness and mass as one other variable to help optimize the overall use of materials. New meteorological modeling tools are becoming very useful for giving us good insight as to what is the wind really doing up at 1 kilometer. Nearly all of the wind data that we have available, the vast majority of it is all recorded down at ground level, but there are balloon data at scattered locations, and the meteorological modeling tools that are used for weather forecasting actually do a pretty good job of modeling the whole of the lower atmosphere. Integration of wind power into tall building needs to take careful account of local flows to avoid vibration effects and reduction in power. It also needs to be a part of an overall multifaceted approach to reducing the carbon footprint of tall buildings. Can't do it on its own. Double-skin facades are being looked at on many buildings, but the physics are complicated and should not be oversimplified. We've developed tools which we think can help look at those processes in detail. The options for implementing natural ventilation in tall buildings can become greatly increased if you can eliminate stack effect through having shafts made at ambient temperature. And in hot climates, there are opportunities to create pleasant, usable outdoor spaces both at height and at ground level for tall buildings. And that brings me to the end of our talk.
Thank you very much. We'd like to thank Peter Irwin and John Kilpatrick from RWDI. Thank you, gentlemen.